ょう。じゃあ、ロスさんからのオプショナルチェーニングの話です。よろしくお願いいたします。
よろしくお願いします。一応英語で発表させていただきますけど、日本語のスライドもありますので、見たい人はぜひ、見ていただけたら幸いですね。So switching to English, my name is Ross Kersling, and today I will be talking all about the journey that optional chaining, the JavaScript optional chaining feature took all the way from being an idea in someone's head to becoming available for use in your favorite JavaScript engine. The whole journey of being specified and also being implemented in my case, JavaScript core as an engine. So a little bit about me. I'm an engineer at PlayStation. And I've been with PlayStation for a long time, but in October, just last month, I moved from San Francisco to Tokyo. So that's been very exciting for me. I'm a reviewer in the WebKit community, and I'm also a delegate to TC39, which I'll be talking about in this presentation. And outside of work, I speak Japanese, I love karaoke, and since the pandemic, I've been enjoying writing songs. So the core question of this presentation is, how does a beloved JavaScript feature come to be? So of course, optional chaining is a very well-received feature, which means that we no longer need to abuse the Boolean AND operator in this way anymore. Which wasn't type safe, but we often felt, oh, maybe it's safe enough. Like this is the lesser evil of a way to go down a long chain and hopefully try to access the last piece of the chain, but we're not sure if we can actually get there. Well, now we have this question dot operator, and that allows us to write code that is correct, concise, and even more performant. But how? How did this come to be? The answer lies in the TC39 process. So for those that don't know, TC39 is the 39th technical committee of the standards body called ECMA International. And we're responsible for ECMA 262, which is the language specification for JavaScript, or as we more properly call it, ECMAScript, because Oracle owns the rights to the name JavaScript, which is always kind of unfortunate. So we typically think of this process as having 4 stages, but there's also sort of this 0th stage. So if you're in the shower and all of a sudden it occurs to you, wait, I have this great idea for JavaScript, and you get out of the shower and you open up a markdown document and you write down your idea and you think about who to present that idea to. Well, that's a straw person. That's stage 0. And anyone can author that, can author their JavaScript idea that they want to present to the committee. Somebody on the committee needs to present it to the committee as a whole and to sort of usher it through the stages of this process, and that's called being a champion. And so when a champion presents an idea and the committee recognizes the problem space, then we have a stage 1 proposal. And what I mean by problem space is that at this stage, we're not concerned with solutions yet. You might not have the perfect solution to begin with, but you recognize a real problem, a real pain point that JavaScript developers have. And that's the really important thing that we're going to want to investigate through this process. If you, on the other hand, have a solution, but you don't have a real problem, that might not be very good. That might not actually be considered a worthwhile proposal. Now, stage 2, draft stage, is when the spec is under active development. People might also start to create unofficial polyfills. They might write spec tests. And eventually we'll get to stage 3, stage called candidate, which is a ready signal to JavaScript engines that we are ready for initial implementation. And those initial implementations will generate feedback. We might find some bugs in the spec. We probably need more spec tests. If we discover something horrible that we forgot to consider, we might even step back to stage 2. That's rare, but worst case, that can happen. Eventually, we'll ship the implementation, we'll ship implementations in at least 2 engines, at which point we can fully accept the proposal. We can make it stage 4, we can call it finished. This means that the spec PR will be merged. The living standard on GitHub pages will now show the new feature, and it will also appear in the next yearly snapshot, so ES 2023, for instance. So how did all of these stages go for optional chaining in particular? It's hard to say where everything began. This feature existed in C# beforehand, for instance. But what's really interesting to remember is that at the very beginning of TypeScript, issue number 16 in July 2014, someone requested this feature. And TypeScript as a rule doesn't want to put itself in direct syntactic conflict with the base JavaScript language. So instead of going their own way and implementing this as part of TypeScript, they worked with TC39 to realize this as part of JavaScript proper. But this, of course, took a long time, and you can see that because this wasn't fixed until issue number 33294. And so in 2016, the straw person was authored by Claude Posh, and the initial champion to present this to committee and reach stage 1 at the beginning of 2017 was Gabriel Eisenberg. Now at stage 1 actually took a long time. We had some real heated discussions on GitHub about both syntax and semantics. As you're probably aware, when we do an optional bracket access, we have to write question dot square brackets. There's still that dot in there. If you were using C#, you could just write question square brackets. And people were kind of like, is there no better way? Do we need that dot? And the reason that we need that is to distinguish it from a ternary, where we might have the ternary question mark followed by the square brackets of an array. And that to determine definitively that we have an optional bracket access and not a ternary would require unbounded look ahead. That's not necessarily a problem for an ahead of time parser, but it is a problem for JavaScript. And so this syntactic solution was kind of the least bad thing that we could do. But as you can see from the 282 comments here, it was a bit heated. Also, semantics-wise, in a language which only has null, which doesn't have undefined, there's a different way of considering this operation, which is that you're propagating null through the chain. But that's not really how we want to consider this. What we want to consider is you're trying to reach the end of the chain. You're trying to determine the value of the last property in the chain. And if you can't reach that point, then you get undefined back. You early out with the value undefined. And the only way that you should get null is if you actually reach the end of the chain and you find a concrete null value. But people had different conceptions of the feature originally, and this was also kind of a heated topic to resolve. And these were some painful discussions. These were some of my earliest TC39 experiences, and some of these conversations were very draining. And the fact of the matter is that sometimes you have a situation where nobody wants to have a particular conversation. It's about an edge case. It's about just a difficult topic that you wish you could ignore. But these topics, we have to face them, and we have to come to a consensus because we have to have a complete feature that has considered all of those edge cases so that we can deliver it to the world, so that we can say this deserves to be part of JavaScript. But unfortunately, multiple champions burned out along the way, not just Gabriel Eisenberg, but also Dustin Savory. And after almost 2.5 years, in June 2019, we finally reached stage 2 under a new champion, Daniel Rosenwasser of TypeScript team. Now, stage 2 and thereafter was a lot smoother. Stage 2 is all about spec polishing and spec review. I was one of the 2 reviewers for this. Ben Coe was my co-reviewer for the spec. And I thought it would be interesting just to show you a piece of the spec. Some of you may not have really looked at the JavaScript spec before, or you might have found it really daunting. It's kind of like a legalese implementation of JavaScript. But let's just take a look at a real quick piece and consider, how does the spec describe evaluating a question.b? So a question.b is an optional expression, and that's made up of a member expression A and an optional chain question.b. And that member expression A, it refers to something, and we want to know the value of that which it refers to. And if that value is undefined or null, well, this is the key piece of what makes it an optional chain. We're going to early out with the value undefined. And otherwise, we're just going to act as if it were a normal dot access of a property. We're going to continue evaluating that dot b, the rest of the chain. So upon finishing stage 2 and reaching stage 3, we're at the point of implementation. And I was actually the implementer of this feature in JavaScript core in WebKit. And so I'd like to walk you through how this feature was implemented in JavaScript core. So you all know that, web applications have a front end. It turns out that JavaScript engines also have a front end, and other compilers as well. JavaScript engines are typically a bytecode virtual machine. And so the backend is responsible for executing bytecode. But we need to get bytecode first. So how do we get from the JavaScript source text to the bytecode? That's the front end. And this has 3 stages typically, and at least definitely so in JavaScript core. The first stage is the lexer. So if we have source code 1 plus 1, white space, of course, does not matter, then we're going to turn that into a token stream, integer plus integer. But of course, our structure there is not just a flat list. There's actually more structure to that syntax. And so we want to make use of the parser to form a tree. In this case, we have a parent node that's a binary operation add, and we have 2 child nodes that are number nodes with value 1. And then our bytecode generator is going to walk over that tree, and it's going to determine that this amounts to exactly 1 instruction, an add instruction, with 2 parameters, 1 and 1. So let's take a look at each of these stages for optional chaining in particular. The first stage is the lexer, which performs lexical analysis, which is to say that we look at the source text and we find all the lexemes or tokens. So indeed, we could say that this process is called tokenization, and the thing that performs it is a tokenizer. And we often do say this, but lexer is a word that's been around for a long time, and it's quite common. There's even another word, scanner, which can be used for this purpose, but I personally think that's even the most confusing of all. Anyway, our goal is to turn a question.b into the token's identifier, question.identifier. And our solution for doing that is to add a new token type called question dot, and then to differentiate question dot from question of nullish coalescing, and the ternary question mark. And this is the only time in the presentation that I am going to show you some C++ code, but I figured that it's actually just as easy as showing this to you in any other format, so why not? At the core of a lexer is just a big switch statement. And so if we are in the case that we've found a question mark, then we're going to ask the question, do we have 2 question marks right in a row? If we do, then we definitely have a nullish coalescing operator. If we see a question mark followed by a dot, we might have optional chaining, but we have to remember that there's one case that's an exception. If we see question dot 3, well, that's not accessing 3 on an object. That is the ternary question mark with the value 0.3. So we do have to rule that case out, but otherwise we've seen a question dot operator, an optional chaining operator, and otherwise we will have the ternary question mark. Okay, so we've got some tokens. Let's turn them into a tree. Now, thinking concretely, on the surface, a question.b looks very much like a.b. This is totally intentional, but of course, these do have a semantic difference between them. And what we'd like to decide is how to build our abstract syntax tree to reflect the difference in meaning between these two expressions. So naively, we often may think of a question.b like a ternary, like a double equals null, then undefined, else a.b. So we're going to need to know a and a.b, and so we might envision some parent node that's an optional chain node and two children. One is a and one is this subtree for a.b. But very importantly, we're going to need to avoid double evaluating a. A could be a getter that performs a network operation, something really expensive. We need to be aware of that possibility. If you just see in surface code a question.b, definitely the user is not expecting a to be evaluated twice. So instead of having a as this separated extra child node, we can just indicate it with a flag. And that's a bit abstract to visualize on this slide, but we can go through progressively the trees that we're concerned with here. So if we just start as simple as possible and just consider the expression a, what does the syntax tree for that look like? Well, it is a resolve node for the identifier a, which just means that a refers to something and we are going to need to resolve what it refers to. If we have a.b, now that resolve node is the first child to a dot accessor node, which is going to access property b on whatever a resolved to. If we have a question.b, this is almost the same. We just add an optional chain node on top and we mark our resolve node as the base of an optional chain. So let's generate some bytecode. But first, let's all make sure that we fully understand what bytecode is. So if you haven't directly interacted with bytecode, you've probably heard of it, and you might have some conception in your head that it's like assembly. And that's true. It's assembly effectively for an idealized machine or a virtual machine. And what it lets us do is it lets us put our code in a straight line. It lets us linearize our code because, of course, humans really appreciate complicated control flow structures and convenient abstractions. But computers at the end of the day are very good at executing a whole lot of simple operations all in a row. And so this lets us get closer to what the computer is actually doing. And we're just making use of, a small set of building blocks, a small set of basic operations. And we can use these building blocks, these operations, without even worrying about CPU architectures, because it's not for the CPU directly, it's for our virtual machine. Now, I do need to mention that if we implement more operations, then we do at that point need to worry about CPU architectures. We need to worry about our physical machines. But if we're just doing a front-end feature, then we can just forget all about that. So basically, it's just human resource machine. I'm not sure if you all have played this game. It's a lovely game that's basically visual assembly, and it's a machine made of human resources. You take a number from the inbox, you perform some calculation, and then you put it in the outbox. So in this case, we're trying to triple a number. So we have this label at the top that we're going to jump back to at the end. So it's an infinite loop. And we're going to take a number from the inbox, and we're holding it in our hand, and we're going to copy it onto the floor in slot 0. And then we're going to take what's in slot 0 on the floor and add it to what's in our hand. We're going to do that again, take from slot 0 on the floor, add it to what's in our hand. And now what we're holding in our hand is a tripled number. So we'll stick that in the outbox and jump back to the beginning again. So that's basically all bytecode is. And we don't need to worry about stuff like this very real ARM instruction, which is a floating point JavaScript convert to signed fixed point rounding towards 0. That might be very important when implementing certain areas of the backend, but we won't need to worry about that when we're just using bytecode. So finally, what should we generate? Well, the semantics here are really just like a try block. A try block, a try statement is a statement, and we have an expression here, which will have a return value, but that's the primary difference. Let's take a look at the paths that we take through these two code examples. So in the first example, foo might throw, so we'll go to oops, and then we'll execute whatever lies beyond, whatever comes after this try catch statement. Maybe foo doesn't throw, but bar throws. Then we'll go to oops, then we'll go to whatever comes after. Maybe foo and bar are both fine, so we don't go to oops, but we still end up in the same place after. We have this little bit longer of a chain below, a.b, question.c.d, question.e.f. So again, there's two places that might be undefined or null. Maybe it's the first one, maybe B is null. So we'll return undefined, we'll go no further in the chain. And then we'll proceed from there. Maybe B was non-nullish, but maybe D was nullish. So we return undefined, we go no further in the chain. Maybe we make it all the way to F, and then we return the value of F, and we don't worry about this undefined value. But one way or another, whatever gets returned as the value of this expression is ending up in the same place. Maybe this whole expression was being used as the argument to a function, but whether we return the value of F or whether we return an undefined constant, that value is going into the function in the same way. So let's take a look at that on the tree. So we encounter this optional chain node, and we're going to push a jump label. We are going to create a place for ourselves to early out to. Then we're going to walk down here, and we're going to see that we have a resolve node, which is marked as the base of an optional chain. So we're going to see what is the value that A refers to. And if it is null or undefined, then we're going to jump to that label that we just pushed. Otherwise, we'll perform our usual dot access. One way or another, once we're done evaluating the whole expression, we'll pop the jump label, clean up after ourselves. And so what does that look like in actual bytecode? Well, this slide might look a little daunting at first, but we'll go through it slowly. It's only 5 lines. I've actually wrapped the a question.b here in a function, get b of a, which is very nice because in the bytecode, it'll allow us to refer to a as arg1. Also, these lines are labeled not by line number, but by byte number. So 7, 10, 15, 17, 20 instead of 1, 2, 3, 4, 5. And we've also omitted the function preamble because we won't need it. So basically the first line, we're going to ask, is arg1 undefined or null? If it is, we're going to perform a jump. That's what the J is for. And we're going to jump, in that case, ahead 10 bytes to byte 17. So if we go to 17, we'll see that we're going to move something. In fact, we are going to load undefined. We're going to take an undefined constant and put it into loc6, local variable 6. Why 6? Who knows? But it's a local variable. And we're going to put an undefined constant into it, and we'll go to the next line, and we'll return that value. If we didn't jump on the first line, then we'll go to the second line. And our comment says here that we're going to load B from the argument. Okay, so again, our target for the load is going to be local variable 6, and we're going to be performing a load based on argument 1, A. But now we have a 0. Weren't we going to encounter a B here? Well, if we look below, there's a little lookup table for identifiers, and it tells us that ID 0 is B. And this is just kind of convenient because an identifier could be a really long, complex string, and we don't want to put that in line in our bytecode. It's just nice to have it out of line at the bottom here. So effectively, this line of code says, look at arg1, load slot 0 from arg1, and put that in local variable 6. And then on the next line, unconditionally jump ahead 5 bytes to byte 20, which again is our return instruction. And this time we will actually return the value of b instead of an undefined constant. So exactly what we were looking for. So is this the end of the implementation? Well, it could be, but I have one more story for you. So sometimes things get a little bit complicated in the way that the JavaScript spec interacts with other specs. So other web specs like HTML, CSS, spec for your favorite web API, these all sit on top of the base JavaScript language spec. And as I say, sometimes these interactions can get kind of interesting. So where this comes up, JavaScript core actually has a bytecode instruction called j equals null, jump if double equal to null. So why did we have to use this jump if undefined or null, this triple equals undefined or triple equals null? Surely I'm not telling you to try and distinguish these in your own code, am I? Absolutely not. But sometimes in the spec and in the nitty gritty details of a JavaScript engine implementation, we do have to worry about such things. It turns out that there is this construct called document.all. This is a legacy array-like object. It's not technically an array, but it's basically like an array of HTML nodes. It exhibits this strange behavior, which is that it masquerades as undefined. So if you do type of document.all, you get undefined. If you do document.all double equals null, you get true. If you do bang bang document.all, you get false. And this is very strange behavior. And I don't know the full story, but as I understand it, the way this came to be is that way back when people used this for feature checking purposes. But browsers didn't actually want people to use this for feature checking purposes. And so browsers themselves reinterpreted this what the JavaScript that people wrote so that the false path would be taken instead, like you don't have document.all actually. But one way or another, this isn't a language feature. So we have to decide how to refer to it in the language spec. And we'd like to just call it cursed because that's what it is, right? But instead we have to use the verbiage having an is HTML DDA internal slot. And an internal slot is just a spec private property. But what does DDA stand for? Well, it stands for document.all. And I find it very amusing just how passive aggressive this naming feels. So I thought you all might find that interesting. And that is indeed the end of our implementation and indeed the end of our journey, because at this point it was quite, we had our implementations, we could present for stage 4, and here is Daniel Rosenwasser presenting optional chaining for stage 4 at the TC39 meeting at the end of 2019. And that glorious spec PR being merged with so many rejoicing GitHub emoji reactions. So I appreciate you all listening to my talk. And if you'd like to get involved in this sort of stuff, I really encourage you to check out the TC39 website because we're always looking for more people to participate. So thank you very much for your time. ご清聴ありがとうございました。
ありがとうございました。すごい楽しかったです。めちゃくちゃ面白かったです。ちょっとこう、なんだろう、そこまで、最初、アイディアのレベルのクエスチョンドットの話から、実装になるまでどういう話があったかっていうことが、僕は本当にすごくよく分かったのと、あと、バイトコードの生成するとかのところで、JavaScript の専用の ARM の CPU 命令がある。あれも知らなかったですね。そういう実装もやってるっていうのが結構知らなかったのと、あと最後のドキュメントオールオプショナルがマスカレード、なんかこう、 アンディファインドがマスカレードされるみたいな言い方をされてたんですけど、
そうですね。
あれってどういうことなんですか？そのドキュメントオールにクエスチョンドットを使うと、それがアンディファインドだったときに、後ろも
アンディファインドのふりをするんです。
ふりをするってこと？なるほど。
そうなんです。マスケレードって打ってふり、なんですけど、やっぱり変ですよね。おかしい挙動なんですけど。
それをちゃんと実装するために、これは HTML の方でのスロットだからっていう、だからっていうのはフラグみたいなのを持っとくってことですよね。あれ、like オブジェクトだったときにはみたいな。すごい、
はい、
すごい
皆さんはやっ
涙
ぱりこんなオブジェクトは使わないでしょう。だから、自由にダブルイコール塗る全然使ってもいいですよ、もちろん普通に。でもまあこういう非常に細かいところも、エンジン側にはあるんですよっていう。
知らなかったことが多かったです。ちょっとエンジンのところの中にもすごく興味を持ったし、割と皆さんなったと思います。本日はどうもありがとうございました。はい。すいません。また引き続き